Okay, so it's a pleasure to have this opportunity to try to review in 30 minutes the progress in machine learning over the last 10 to 20 years. So the plan here is I'm going to focus just on the basics and begin with a review of those, then discuss the big step forward with deep learning, but also pay equal attention to the framework of probabilistic modeling. And then I'll try to focus on the weaknesses of both of these paradigms in terms of the research challenges. I did want to touch briefly on anomaly detection at the end, and then provide my suggestions for the capabilities matrix. So, of course, the basics in machine learning is the area known as supervised learning, and we assume we're given a set of training examples, which are typically pairs of some sort of a description, X, I, say a feature vector in d-dimensional space, and a class label, or it could be a real valued response. And the goal is to learn a classifier or a function that maps from the d-dimensional feature space to the class labels. So the sort of paradigmatic example would be optical character recognition or handwritten digit recognition. And so these are some shots from the MNIST character recognition data set. So the input is a 32 by 32 bit image, or pixel image, and the output is one of the 10 digits. So there are two fundamental paradigms that have been explored in machine learning. The first is the probabilistic modeling paradigm, and then the second, I'm coining a term here, but the end-to-end function learning paradigm. So the probabilistic modeling paradigm, a very simple example of this is Fisher's linear discriminant. So what we do is we build ourselves a probabilistic model of how the data is being generated. And in this particular case, we can describe it by this little graphical diagram here. We imagine that whoever's generating the data first chooses one of the digits that they want to write with their handwriting, and they do that from some discrete distribution, P of y. And then they decide what actual pixels to produce, and a very, very naive model of that would be a multivariate Gaussian over the pixels. So there would be some mean pixels for, say, the digit 3, and then some covariance matrix over those pixels. And if we're willing to assume that all the covariance matrices are equal, then we get Fisher's linear discriminant, which is, I don't know, 1930-ish. So the learning process in this paradigm is just fitting the model to the data, which in this case is extremely easy. But classification, that is making predictions, then requires us to do some probabilistic inference, because we don't observe y first and then predict x. We observe x first and we have to infer y. Of course, fortunately, there's this thing called Bayes' theorem that lets us do that. But more generally, in very complex models, we may need to do probabilistic inference both during the model fitting process and during the prediction process. The alternative paradigm is the end-to-end function learning paradigm. And this is a picture of one of the early deep neural networks, a convolutional neural network developed at Bell Labs back in 1998. That is the sort of granddaddy of all the things we have today. So the idea is that we define a space of parameterized functions, parameterized in this case by a vector theta, and a loss function which says how bad is it to output y hat when the real answer is y. In this case, we'd usually use 0, 1 loss. So if you get it wrong, you have a loss of 1. If you get it right, you have a loss of 0. And then we need to solve an optimization problem, which is to find the setting of the theta parameters that minimizes the sum of the losses on our training data. And we usually need to include another term which penalizes the complexity of the parameters, because we typically have a highly over-parameterized model class with millions of parameters potentially, and we don't usually have that many degrees of freedom in our data, even with big data. Then to make predictions is computationally very cheap, because we just have to evaluate this function in the forward direction. And nowadays we do that on a GPU, so it's easy to put into a phone, for example. Well, there's been a lot of progress in both of these paradigms over the last, say, 15 to 20 years. The first thing is in the probabilistic modeling space. There's been the development of very rich probabilistic models. We don't have to assume everything's Gaussian anymore. We have, for instance, complex mixture models. So it could be Gaussian mixture models or hidden Markov models. And this was promoted a lot by the development of probabilistic graphical models, and perhaps Udaya Pearl's book is the best known source for that. There's a development also of non-parametric models where the number of parameters can grow or shrink depending on the amount of data. And I think a lot of people would point to the development in the statistics community of Dirichlet process mixture models. And then in the last 5 years, there's been a real flowering of something known as probabilistic programming. And DARPA has just finished a program in that area. And two examples of that would be the language Church, which is basically a scheme-like language in which you can describe a probability distribution by writing a program. So it's an executable program, but the executions are stochastic, and the distribution you're describing is the distribution over all possible executions of the program. That's only interesting because you can then say, I want a condition on the output of the program, tell me what the inputs had to be in order to produce those outputs. So you have to be able to sort of run the program backwards, which is quite interesting. And perhaps the most popular probabilistic programming language is known as STAN, and this was developed at Columbia in Andrew Gelman's group, and it's just had a huge uptake in the statistics community. Of course, it's not enough to write beautiful languages. We have to actually reason with them. And so there's been similar big advances in probabilistic inference methods, starting with belief propagation, which was in Pearl's original book. But then variational inference techniques were imported from physics, as were Markov chain Monte Carlo techniques. And the idea of MC is you define a Markov chain whose stationary distribution, if you run it long enough, is the desired probability distribution you're trying to model. And another notable advance there has been Hamiltonian Markov chain Monte Carlo, which is the inference engine underlying STAN. And that has led to being able to create Markov processes that converge very quickly to their stationary distribution. Interestingly, it uses the derivative of, say, the likelihood function. And to do that, it uses automatic differentiation techniques. So you've written your program, it's automatically differentiated to get the derivatives. So what are the strengths of the probabilistic modeling paradigm? Well, one of the big things, I think, is that it can represent knowledge that we might have about the problem. So coming back to Rama's question about geometry or physics, we can put that into the probabilistic model. We can also represent and reason about latent variables, which I think is very important in intelligence analysis. And models are interpretable if they're identifiable. So we have techniques for figuring out whether those latent variables can be uniquely reasoned about. And then finally, we get calibrated assessments of our uncertainty in our conclusions, conditioned on assuming the model is correct. So just as an example of using latent variables for, say, multi-sensor fusion, we might have the true phenomenon be some sequence of variables here. It might be, say, the location of a person we're trying to track or something like this. But we don't observe that directly. Instead, we observe some noisy signals. Maybe one of these is from, I don't know, GPS and another is from computer vision or something, or financial transactions. So the coding here is that the gray variables are the ones we observe and the black variables are the ones that we just need to make inferences about. So now let's turn to the function learning side. Sort of similar things have happened there. So there's been development of very expressive function classes, starting with nearest neighbor methods, but then the development of support vector machines, decision tree and decision tree ensembles, the multi-layer perceptron, which we would now think of as just a very shallow neural network, convolutional neural networks, long short-term memory networks, residual networks, and right now we're in the midst of sort of giant hackathon in the field as people are experimenting with all kinds of different models. Another thing we discovered along the way is that ensembles are very powerful, and so we have various methods for creating those. So even with deep networks, typically you can get some boost in performance by training multiple networks and having them vote, which is sort of astonishing because the number of parameters in those models is mind-blowing. Well, of course, again, it's not enough to come up with beautiful languages for describing your models. You need to solve the optimization problem of fitting them. And there's been a lot of progress there, mostly by machine learning people making very good friends with people in operations research and optimization theory. So Maybe the unique contribution of the machine learning community was the development of boosting, or something known as functional gradient descent. But we've imported convex optimization techniques. Stochastic gradient descent has been explored from many angles, and there's an exciting development there called Nesterov acceleration that gets us to very rapid convergence. And many techniques underlying the recent progress in deep neural networks that I won't go into. And I just wanted to address this question about confidence assessment. So one interesting framework that's come up recently there is something known as conformal prediction, and it gives you point-wise confidence assessments of the predictions of the model. Unfortunately, it does, just as in probabilistic modeling, we have to assume the model is correct. Here, we don't have to make that assumption, but we do have to assume the data are exchangeable, or near IID, which we know is false. Both of those things are false, of course. We know our model's wrong, and we know the data really isn't IID. So what are the strengths of function learning? Well, with sufficient data, it's usually more accurate than the probabilistic modeling framework. So if you look in, some of you may know about Kaggle.com. They run machine learning competitions, and those competitions are virtually always won by some function learning approach. And I think the reason is that if you have enough data to fit them, the flexible function classes that in deep nets or boosted tree ensembles make many fewer modeling assumptions. They also require a lot less model development effort, and machine learning people really don't like to think about modeling, so they would just rather point a black box at the data and have it run. And they're very fast at runtime. Well, the general methodology, right, for building a machine learning system involves these steps of data acquisition and then feature engineering to try to transform the data into the form that will match the assumptions of your model. And then model design, model fitting, and model evaluation. Well, usually about 90% of the effort goes into that first two steps, particularly the feature engineering step. And so the big advance of deep learning has been to automate that feature engineering step. So if we look at computer vision before, say, 2012, the whole field was using hand-designed or human-designed features. So we had these cool things called SIFT descriptors and histograms of gradients. But after 2012, we switched to convolutional neural networks. And here, for instance, is the top 5 error rate on ImageNet, which is a challenged problem with 1,000 object classes. And we can see that with the introduction of deep learning, we went from error rates in the 25% range down to error rates in the 7% range. So it's been really a dramatic improvement. So the key finding is deep nets can design better features than we can design by hand. So this is particularly valuable when we're doing a signal-to-symbol type of transformation, right, where we have low-level signals and we need a high-level interpretation, and there's a big gap between them. And we don't know how to engineer the features along the way, but we can use this deep learning technology to do that. On the other hand, if you have data that is already more featureized, let's say like medical records or, well, that ignoring text, but like physical measurements that can be treated as variables themselves, then there's probably less to gain by using the deep learning technology. And the technology is not easy to apply. So often it's best to avoid in those kind of settings. Okay, well, similar advances have happened in speech recognition, right? Before 2012, the field was using probabilistic graphical model techniques, so hidden Markov models and Gaussian mixture models. But after 2012, people went into deep recurrent networks, and we've seen similar advances, similar reductions in the word error rate. For Google reports that they had a 23% word error rate for their telephone speech recognition system, and now they reported this year they're down to 4.9%. Well, it turns out that there's a collection of weaknesses shared by both of these paradigms, and I want to review 5 of them. So the first one I want to think about is the problem of the assumption of stationarity. So the whole idea of learning from data is that we can collect data that's going to be representative of the queries that we're going to have to answer. And we have lovely machine learning theory that tells us if the test queries are drawn from the same distribution as our training data, that is, our training distribution and our test distribution are the same, And if our learned function or learned probabilistic model is accurate on the training data, then with high probability, it will also be accurate on those test queries. So this is a beautiful thing, but the problem is it does make this assumption of stationarity. And we see violations of this everywhere, essentially. Right, so one that natural language people are very familiar with is that if you're trying to build a parser, you're probably going to be using the Wall Street Journal corpus, the Penn Tree Bank. Well, that's trained on the corpus, but maybe you want to use it on social media, and so those are vastly different in their structure. Another, of course, is that there are trends in the data. So any kind of financial transactions, we might train on data from the 1990s and then try to test on data today, where we now have cryptocurrencies. The world population has changed. The economy is functioning in different ways. And then it was mentioned before, the problem of adversarial learning, that if our adversaries are criminals, for example, they're constantly changing their tactics in response to our efforts at enforcement and surveillance. The second weakness is the big data requirement, especially for deep learning, but in general, the more complex the problem you want to solve with machine learning, the more data you're going to need. So in many applications, there is very little data available. In natural language processing, this problem of low resource languages has been attacked a lot, and Boyan here has been funding quite a lot of research in that area. But we can see other situations, novel weapon systems, or also just trying to make inferences about a small subpopulation within a much larger population, where although we might have millions of people and billions of training examples, maybe for that subpopulation of interest, say young people vulnerable to being radicalized, we don't have very much data. In the computer vision setting for object recognition, a very promising direction is what's known as fine-tuning deep networks. So you can take a deep network that was trained on, say, ImageNet data, and then fine-tune the final layers using a relatively small amount of data. So I have colleagues, I do a lot of work in ecology. I have colleagues that have been looking at recognizing insect species, okay, from microscope images. This is a very different kind of image than you would have in ImageNet, and yet surprisingly, you can get excellent results, like 90% plus correct, just by fine-tuning the ImageNet networks. The third problem is biased data collection, and this is something that the machine learning community has only recently woken up to, although I'm sure every intelligence analyst could have told them that this is a problem. The data are often collected through some biased process, and an example I'm familiar with is we send bird watchers out to try to get observations on bird species. Some bird species are really easy to see. You know, cardinals are bright red, some songbirds just sing a lot, but others are dark brown and hide all the time. And if you just use the number of sightings from bird watchers, you might think those species are highly endangered because nobody can seem to find them. But in fact, there might not be a problem. Another example that's been a lot in the news lately is training criminal justice classifiers, say, to predict recidivism. If we use the current prison population to do that, then we're replicating whatever biases might exist in the current legal system. And another instance of this kind of biased data came up in the Google photo application. So some of you may have seen Google has a photo sorting app, and it mislabeled some black people as gorillas. Because it has insufficient data, training data for them. Now, it'd be interesting to look at what were the data sets that they used to train this system, but clearly there was not enough data to correctly handle this subpopulation within the larger training set. There are, in the probabilistic modeling framework, there are good ways of dealing with bias sampling. So to take another example from species surveys, there's something known as the occupancy model that was developed out here at Patuxent USGS lab. And the idea is, just briefly, that we're really interested in whether species are present. So Z sub I is true if a particular species is present at a particular site, and these are the features of that site. So we're very interested in this model, which is the habitat model for the species. We send out observers, say capital T observers. Each one of them, though, only has a certain probability D sub IT of detecting the species, and so we get these very noisy observations Y sub IT. And so it is possible to fit this model to the data and figure out, learn the detection probability model and also the species habitat model simultaneously. So that's just one simple example. Another example is there's been a lot of work in crowdsourcing, of course. We use Amazon Mechanical Turk and so on to get people to rate things or to rate movies. So the data typically looks like a rater by item matrix. But the items have unknown different amounts of difficulty for the humans to rate them. Say we're asking them to label the objects and images. Also, the raters have unknown reliability, and some of them might be actually just guessing randomly or even behaving adversarially. So we can build a probabilistic model that tries to model the reliability of each rater and the difficulty of each item, and it looks something like this, and estimate both simultaneously. I've lost track of my count. Fifth issue is the brittleness of end-to-end training. So it's been mentioned, this problem of adversary examples. How am I doing for time? Let's see. Okay. Okay.
So that we'll have 5 minutes for question and answer.
Great. So one of the early papers showed that if you take a picture of a panda, which was classified by an ImageNet system with 57% confidence, so wasn't super confident about the panda. But given that there are 999 other categories, that's still pretty high confidence. And then they add what appears to be random noise, but is actually very carefully optimized perturbation of the image. And they can convince the system that it's a gibbon with 99% confidence, even though to our eyes the image is unchanged. And similarly, there's another group that was at University of Wyoming that was able to use genetic algorithms to come up with these crazy patterns that also would be classified with high reliability. And there are even people selling T-shirts now that will make you be recognized as a school bus and things like this. More as a joke, of course. But there was stuff just in the news this week about some guys, I think in Germany, that had developed a set of stickers you could put onto a stop sign, and then the self-driving car system would think it was a speed limit sign instead. So this is a real problem. Another example of brittleness is known as the problem of open category recognition. So we train our system on 1,000 categories, and the thing is that our systems basically have the mental model of the world that there are only 1,000 kinds of things in the universe. Right? So if we show it some new object that it's never seen before, maybe an iPhone or something, it will fit it into one of the 1,000 bins it knows about. It might be not confident, but it also surprisingly might be quite confident because the image might be very far away from all of its so-called decision boundaries. So this is a plot from some work by Shirer and colleagues, where they're comparing a measure of system performance against what they call openness, which is basically the amount of test images that belong to new categories. And we can see that the sort of standard end-to-end training systems performance falls off quite quickly as we introduce these. They've got some new algorithms, something called a Weibull SVM, that's able to, it doesn't suffer quite as much from this. But this is an ongoing challenge for us. The last thing I want to mention is verification, validation, and monitoring. So the machine learning, and maybe I'll just speak for the machine learning community, we've been totally focused on how accurate can we make our systems. And we've really ignored all of the other illities that engineers might be concerned with: testability, diagnosability, reliability, maintainability, and so on. And so we really need new methodologies for establishing trust in these machine learning systems. Or maybe I should say more generally, we need to somehow bring together the sort of software engineering, reliability engineering communities with the machine learning community, because it's happening in some companies, and Google has published some very interesting internal coursework and guidelines that they've developed. But in terms of funding priorities, I think if there's a way we can encourage those communities to get together, this would be very important. So there are some projects, things happening now, but things like verifying that our training data really is representative of the input domain. What would be some methodologies for that? Verifying the absence of adversarial examples within a certain distance of the data. There have been some papers using model checking, so logical inference, to address that question. And there's a lot of existing work on how can we detect that the input distribution is changing and at least raise the flag that our system is probably not going to work well, and even adapt to those changes. Although, let me take a slight detour into the question of anomaly detection. This is a problem that has not been studied that much in the machine learning community, but it's currently becoming more prominent. So let's assume we have a collection of data that is a mix of what we call nominal, to avoid confusing it with the normal distribution, nominal data and anomalous data. And we'll assume these are IID points, and our goal is to detect the anomalies. So over the last 10 years, particularly in the data mining community, many good algorithms have been developed for this problem. And one place they're being applied is to actually screen for adversarial and open category inputs, say, to computer vision systems. So like the Weibull SVM actually uses something called a one-class support vector machine as an anomaly detector in front of the classifier. So I was a performer on a DARPA program called ADAMS for detecting insider threats, and I have to show off our results. We had data from a corporation that had 5,000 employees, and then a red team had been hired to insert onto some unsuspecting employees additional desktop activity data where they were acting out some kind of an insider threat, a data exfiltration threat or intellectual property theft or something like this. And the arrows are for the Oregon State University algorithms. So in the June 2013 challenge, I'll show you the good case, right? We did very well. But the techniques were generally working well. If you're interested only in, say, the top 100 hits, if you're interested in finding 99% of all the anomalies, that's much harder. But if you're interested in the most obvious ones, we can do that. And we have ways of incorporating analyst feedback to do that as well. So I think that's part of the key to making progress on many of these things. Okay, well, let me quickly do my capabilities discussion. So I think current capabilities we have, we can apply deep learning to signals type data if they're stationary and if we have enough training data. We can rapidly adapt to new problems using fine-tuning, and to some extent with anomaly detection, we can detect unusual behaviors and potential threats. In the near term, I think we are making good progress on this open category classification problem. We're making progress on biased and untrusted sources, and so I hope that we could begin to automatically detect, or at least have tools for auditing, the bias in our systems. Maybe building reusable libraries of models of information sources. A big challenge is anomaly detection on time varying and network data. And then I think we'll have some initial model methods for validation and system monitoring. And then in the longer term, really successful defense against adversarial examples is going to require a lot more work. And another huge challenge is integrating large knowledge bases such as knowledge graphs with machine learning. We really don't have ways to do that yet. I think it'd also be very interesting to capture the meta-reasoning to develop and test hypotheses about data source reliability. So a good analyst can look at an outlier and say, that's strange, I wonder if the definition of this feature changed, and then they can compare other things from that same information source and make inferences about what's going on that our current systems cannot. And so I think another challenge is multi-scale and one-shot and zero-shot. Our current computer vision systems, for example, if we just change the dimensions of the image slightly, the performance degrades quite shockingly. And that's certainly true for anything else in, say, reinforcement learning. Okay, done.
Thank you. I guess if you have any questions, please push this button so it can be recorded.
How much is the learning limited by the computational horsepower?
Well, the computational horsepower was really critical to being able to process more data. So in some sense, it has been limited by that. And of course, this is why NVIDIA's stock is way up, and also we see the Google developing specialized things like tensor processing units, and other companies in that same space. So improving the hardware there's a lot of headroom there. I think we can make a lot of progress there, and the better the hardware, we'll use it up with data. So we're the machine learning guys are like sponges for this.
Yeah, thanks, Tom. Really wonderful overview. Thank you. throughout that, all of your survey of the technology and the examples of the use and even overcoming challenges seem to be limited to application of machine learning within a particular modality of data. And considering the focus of this workshop, I wonder if that implicitly says something about the readiness of machine learning to handle multimodal data, heterogeneous data sources, sort of on their own.
Yeah, I would say from inside the machine learning community, you're exactly right. We are develop point solutions to a single data source. I'm hoping that maybe some of the computer vision and natural language folks can say a bit more about fusing that with multiple sources. But you're absolutely right that if you're looking for expertise in that, probably the machine learning community is not the place to look first. Yeah.
Any other questions? Yes, please.
Can you say just a little bit more about what you mean by multi-scale?
Let's see if I guess I should stand here.
Can you repeat the question?
So the question was, could I say a bit more about multi-scale? Well, let's think about something like change point detection. Typically, our systems there you would have some sort of a pair of sliding windows over time of a fixed length, and you would compare the distributions in those two windows. But that would only detect changes that are happening at a certain rate, and you would really need methods that would do that at many different scales. And then make the appropriate compensations. And the same goes, I think, for object detection in computer vision. You're basically usually sweeping some sort of a window across the image, and you're going to find objects of a certain size. And there has, I would say that the best work in multi-scale is there. But the same in reinforcement learning, we usually assume there's a fixed time clock ticking, and we get to make one action every so many seconds. If you tell us that we're going to be making actions over multiple orders of magnitude, the things just don't work at all. So.